after studying this, you will learn more examples of molecules belonging to different point groups, learn more examples of type 3 dihedral point groups, that is D group, DN, DNH, DND point groups. Learn more examples of type 4 point groups, that is cubic point group, special point groups, that is TD, octahedral, icosahedral. Examples of some more special point groups, C infinity V, D infinity H and KH will also be cited to you. Recognize the symmetry elements present into the molecule. Have the knowledge that the presence of certain symmetry element require the existence of other symmetry elements. Know the scheme of classification of the molecules into point group. Have practice of finding the point group into the molecule. Now, in earlier module of classification of the molecules into point group, I have discussed with you the type 1 and type 2 point group, and various examples of these have been discussed with the help of the model. In earlier model on classification of the molecule, we have come across the various types of point groups for the molecules. Number of examples of each point groups were given and explained in detail. In this module, we will continue with this classification and will take up other types of point groups. Only few examples will be taken and discussed. Example of type 3, dihedral point group, that is D group. In the molecule of the type 3 dihedral point group, there are CN axis and NC2 axis perpendicular to CN axis. That is, if there is a CN axis, there must be NC2 axis perpendicular to this. Point groups belonging to these categories are DN, DNH, DND point group. Let us discuss each of these separately. First, let us take DN point group. That is, we do not have only CN axis and NC2 axis in this molecule. Molecule belonging to this type only have CN axis and NC2 axis perpendicular to the CN axis, and no other symmetry elements are present in them. Few examples of these types are shown. These are cation COEN thrice 3 positive, twisted biphenyl, that is, this belongs to D2, then twisted ethylene, perchloro triphenyl amine, twistane, Gauche form of ethane. These are shown over here, and all these have CN axis and NC2 axis perpendicular to each other. Now, some of the point groups of these are given, that is COEN thrice 3 positive, it belongs to D3 point group. Various forms, various configurations of this molecule is shown, and C3 axis and C2 axis are also shown. So, these molecules in this slide, they belong to DN point group, and the order of the DN point group is given. That is, first is D3, then D2, D2, D3, D2 and D3. Now, what happens if besides CN axis and NC2 axis we have some other symmetry elements? Let us take DNH point group. Molecules belonging to DNH point group must have CN axis, NC2 axis perpendicular to the CN axis and sigma H. These symmetry elements generate all symmetry operations which belong to DNH group. Presence of these symmetry elements automatically require the existence of n sigma V into the molecule. If CN axis is of even order, its combination with sigma H generates I. Hence, the elements of DNH point group are E, C2, NC2, sigma H, I, Sn. And if CN axis is of order odd order, then the elements of the groups are E, C2, NC2, sigma H and S2S and N sigma V. The order of the group is 4 on. Some example of the DNH point group are shown as over here, and all these molecules have NC2 axis and CN axis and also sigma H. That is, the examples are ethylene, naphthalene, PTCl4, trans PTCl to Br2 and cyclopentadienyl. For naphthalene, let us take this example of naphthalene over here. This molecule which I am handling over here, that is, it is at my palm. So, this my palm is the plane of the molecule, and this molecule has C2 axis like this, that is bisecting the bonds, and another is along this, and third will be perpendicular to this. So, in this molecule, if this is my C2 axis, I have n C2 axis perpendicular to this, that is in the plane of the molecule, like this and like this. And if this is C2 axis, then this plane of the molecule is perpendicular to this C2 axis. So, this molecule has this C2 axis, and then there are n C2 axis perpendicular to this, and this is the plane of the molecules. So, this molecule goes to D2H point group. Like this, you can take up any other molecule, PTCl4 square planar molecules, you can find out it belongs to D4H group. Similarly, I can take the benzene ring. Now, if I take this benzene ring over here, and then we can find out what is the point group for this molecule. That is, if I take this is the benzene molecule, and if I put it on my palm, this is my C6 axis. It also has C2 axis along this. Now, if it is a C6 axis, there are n C2 axis, 3 along this carbon-carbon, like this and like this, and 3 in between these bonds, like this and like this. So, this molecule has C6 axis and n C2 axis into the plane of the molecule. So, this molecule goes to D6H point group. Like this, you can take any other pentagonal molecule, you can find out, that is, if it contains CN axis, NC2 axis and sigma H into the molecule, then it goes to DNH point group, and n value of n depends upon the order of the principal axis. Let us take DND point group. Molecules belonging to the DND point group must have CN axis, NC2 axis perpendicular to the CN axis and sigma D. The dihedral plane lies in CN axis, but bisects the angle made by perpendicular axes. The order of the group is 4n, but order changes with the order of the principal axis of rotation. For n is equal to odd, symmetry elements in this group are Cn, NC2 axis and sigma D, S2n. And for n is equal to even, the symmetry elements are S2n, NC2 axis and sigma D. Examples of molecule belonging to the DN point groups are given. These are quest tetrahedral, CS2Cl4, allene, staggered ethane and acid molecule as shown. Now, in allene molecules, the dihedral planes and C2 axis are shown and mentioned, that is where from the dihedral plane passes. In allene molecule, if I put the molecule in a rectangular box as shown over here, my C2 axis will pass along in between the faces as shown, and sigma D will pass from the diagonals. Take the top diagonal, front diagonal, then front edge, then go to the back lower edge. Front edge, top one, then the lower edge, back one, and that plane passes that is that plane divided this HCH bond angle, and it contains 2 of the hydrogens, and these are shown over here. So, in this D&D molecules we are having CN-axis, N2-axis and sigma D into the molecules. These are clearly shown with the help of the diagram. Now, examples of type 4, that is cubic group or special point group. These point group discussed so far contain only one higher order axis. Cn axis is greater than 2. Now we will deal with the molecules which have more than one Cn axis of higher order, n is greater than 2. The set of symmetry elements that are obtained from the combination of several higher order axes correspond to the symmetry of the regular polyhedra. All the faces of regular polyhedra have same regular polygon shapes. The angle and edges have same dimensions. There are 5 types of polyhedra which are shown, and these are highly regular polyhedra. So we can place them into different special point groups, and which belong to this category are T, TH, TD, O, OH, I, IH and so on. Of these point groups, only common point group we generally come across are tetrahedral, octahedral and icosahedral. Now, tetrahedral point group, in this point group molecules have 4 C3 axes along the body of the diagonal of a cube if we inscribe the tetrahedron in a cube as shown in the diagram. The center of the cube is the origin of the coordinate system in which the coordinate axes are parallel to the sides of the cubes as shown. The symmetry operation of TD point group are E8C3, 3C2, 6S4, 6 sigma Ds. 3S4 coinciding with the Cartesian coordinates and are taken as the principal axis. The 6 sigma Ds bisect the angle between each pair of C3 axes. The order of the group is 24. Examples of molecule belonging to the TD group is given. These are the various examples, and also you can cite the common example is CH4 also. The next point group is molecules which have 3 mutually perpendicular C4 axes which coincide with the Cartesian coordinates, that is coincide with XYZ axis, and point of their intersection is origin. Its symmetry operation are E8C3, 6C4, 3C2, 6C2, 6 sigma V, 3 sigma H, I, 6S4, 8 sigma H. That is, this belongs to our octahedral point group. So, octahedral point group is a highly specific point group, and in the diagram an octahedron is inscribed into a cube and various symmetry elements C3, C4 etc. are shown into this. Now, example of the molecule belonging to the octahedral point groups are given. These are MnCO6, PtCl6, PF6, SF6, ALF6, 3 negative. All these are belonging to the octahedral, that is central atom surrounded by 6 ligand, identical ligand, gives us the octahedral point group. Besides this, you can cite large number of other examples belonging to the octahedral point group. Now, icosahedral point group, this is highly symmetrical molecule, and the molecules belonging to this are rare. Molecules with icosahedral have 20 triangular faces, and dodecahedral 12 pentagonal faces belong to the icosahedral point group. The B12 S12 2 negative 9 is an example of regular icosahedral as shown. The symmetry operation in icosahedral are given as shown. Order of the group is 120. Some more example of icosahedral are dodecahedron and fullerene, which are given. Now then we come across with special point groups, linear molecules. All linear molecules belong to C infinity V or D infinity H point group. If the linear molecule has center of inversion, that is a symmetrical molecule like carbon dioxide, like this, then the molecule belongs to D and H point group. For example, hydrogen, H2 molecule, CO2 molecule, C2H2 molecule, nitrogen, N2 molecule, all belong to D infinity point group. These have two C infinity axis, and like this many other which are shown in this over here. Now, non-symmetrical linear molecules which lack center of symmetry, such as heteronuclear diatomic molecule, HCl, CO, NO, HD, HF, SCN, SiH, KH, Sc, etc., they belong to C infinity point groups. And these molecules also have large number of symmetry elements present into this. And these two examples of C infinity, that is the D infinity H point group into the molecule. Now then we have a special point group known as the KH group. This point group characterizes the sphere. This symmetry is possessed by all free atoms. All possible symmetry elements belong to this point group. Free atoms, hydrogen, deuterium, helium, chlorine, calcium, etc., they belong to these point groups. And the figure of a sphere with XYZ axis is shown, and these spherical molecules or atoms, they belong to the KH point group. Classification of the molecules into point group. The success of the quickest method of classification of the molecules into point groups depends upon one's ability to recognize the symmetry elements present into the molecule. This skill can be developed by continuous practice. Before going through the scheme of classification, it is very necessary over here that you should be familiar with the shape of the molecules, and the sum of the shape of the molecules are given, and these are as per VS-EPR theory. Now let us, for example, show some of the shape of the molecule. If you have MX3 planar molecule, that is, we can have a planar molecule of MX3 over here in this. This is my MX3 planar molecule. Tetrahedral MX4 is well known to you, and the square planar tetrahedral molecule is shown over here. Now MX4 is this type. Now MX5 molecule, it can be trigonal bipyramid or square pyramidal. This is square pyramidal molecule with MX this 5, and this is trigonal planar molecule with MX5 like this. This is your MX5 trigonal polymer. So MX5, it can be square pyramidal or it can be trigonal bipyramidal molecule. Like this, it is necessary that you should be well aware of the shape of the various molecules before going into the scheme of classification. Now there are generally two schemes of classification which can take, but two ways of classification I will discuss, and these will be the quickest way of going through the molecule and finding its point group. First, very common scheme that goes into 5 steps. Now that runs as follows. Take the molecule and see first whether the molecule belongs to special point group, that is very high symmetry point groups, TD, octahedral, icosahedral, C infinity V, D infinity H. All these points groups have been discussed earlier. So this is the first, that is you can look out whether it is a linear molecule, tetrahedral molecule, octahedral molecule or icosahedral molecule. For all the remaining, that is if the molecule belongs to this special point group, leave them. If it is not there, then for all remaining molecules, find whether the molecule has rotation axis of any order, CN axis of any order. If answer is yes, go to step 4, otherwise go to step 3. That is, if molecule does not have CN axis of any order, then the molecules can be, according to step 3. Molecule does not have any symmetry elements, goes to CN point group. Molecule has only one sigma, goes to CS point group. Molecule has only center of inversion, molecule goes to I. Now, if the molecule has CN axis, look for NC2 axis perpendicular to the CN axis. If these are there, go to step 5. Otherwise, now look for, if NC2 axis perpendicular to CN are not there, then look for whether the molecule has sigma V, sigma H, no symmetry elements, or only S2N collinear with CN axis. If sigma V is there, it is CNV point group. If sigma H is there, it is CNH point group. If no other symmetry element except CN is there, look for whether it has S2N axis collinear with CN axis. If it is yes, that is, if it has SN axis, then the molecule goes to the S2N point group. In step 5, we look the molecule. If CN axis is there and then NC2 axis are there, molecule belongs to the DN point group. After this, we will look, if the DN point group is there, molecule has some sigma H or not. If it had, molecule goes to DNH point group. If molecule besides DN group has sigma D also, point group is D and D pi group. These are, if neither sigma nor sigma D is there, molecule belongs to DN point group. So these are the 5 points in which you can simply look up whether the molecule belongs to the which point group. See whether it belongs to special point group, that is linear molecule, octahedral, tetrahedral, icosahedral. If it is not there, look for CN. If CN is not there, look for no symmetry element, I or sigma. If the molecule has CN axis, look for NC2 axis. If NC2 axis is not there, then look for sigma V, sigma H or no symmetry pel, or also look for SN axis coinciding with CN axis if it is no other symmetry element is there. Then if all are besides CN axis you have NC2 axis, then go to the DN point group, look for sigma H and sigma D. So this is some special or easy scheme. Now I will take you through a flow diagram, flow chart scheme, and this flow chart scheme again is very easy. At each and every step in the scheme of classification, you will be asked the question in yes or no, and these are the answer to each question will take you to the next question until a point group is finally determined. The first question is whether the molecule is linear or not. If answer is yes or no, to this will direct you to the next question and so on. Presence of each and every symmetry element must be verified before you are certain about the point group of the molecule. That is, it is very important that you must know this symmetry elements present into the molecule.
To the lowest symmetry. Now from this does not tell you all the symmetry elements in a group for which you need a character table. This will just give you a gross idea regarding all these things. Which molecule is more stable, which is having 4 symmetry elements or 6 symmetry elements, just like C2V have 4 symmetry elements, C3V has 6 symmetry elements, D4H has 16 symmetry elements, OH has 48 symmetry elements, out of which the molecule is more stable. The molecule that has most symmetry elements is the most stable molecule. Now, we will try to determine the point group of a molecule with the help of a flowchart. First, the point group defines what type of symmetry elements an object or molecule possesses. We will try to see is the given molecule is a linear one. If our answer says yes, we will try to see does it have any inversion center with it. If our answer is one more time yes, then we will simply say that our point group is D infinity H. If our answer says it does not have any inversion center, then we will say our point group is C infinity V. As I have asked our previous question, does it linear? If our answer says no, it is not the linear one, we will try to see is it highly symmetrical? Is there more than one CN axis where n is more than 2? If our answer says yes, we will ask one more time, does it have any inversion center with it? If our answer says yes, we will try to see does it contain C5 axis with it. If our answer says one more time yes, then our point group will be IH. Otherwise, we will say our point group is simply OH. That means octahedral. Inversion, further go back to the previous question, does it contain any inversion center with it or not? If it says no, our point group will be simply tetrahedral. Go back to the previous question. If it says no, that means we will ask does it have a rotation axis? That is there any CN axis? If our answer says yes, we will try to find the principal rotation axis, the CN with the highest value form. That means we will see the highest order CN axis, and that is NC2 is perpendicular to the principal CN axis. If our answer says yes, we will try to see is there any horizontal plane, that is sigma h plane. If one more time yes is there, then we will say D and H is our point group. If our answer says no, we will try to see is there any sigma d plane. If our answer says yes, that means our point group is D and D. Otherwise, we will simply say our point group is Dn. Go back to the previous question. If our answer says no, there is no principal axis of rotation. Is there any horizontal plane, that is sigma h plane? If our answer says yes, then we will say it is having C and H point group. Otherwise, we will try to go for the no part where we are asking is there any vertical planes are present, that is sigma v planes are there. We will say yes, then our point group will be C and V. Otherwise, we will ask is there any S2n improper rotations collinear with Cn. If its answer is no, then our point group will be Cn. Otherwise, we will say it is simply S2n point group. Go back to the previous question, does it contain a rotation of axis, that is Cn axis? If our answer says no, then we will ask is there any inversion center with it? If his answer says yes, then our point group will be Ci. If it says no, we will try to ask is there any sigma planes present? If his answer is one more time yes, we will say that point group is Cs. Otherwise, we will say point group is C1. So from this flow chart, we can easily conclude that for a linear molecule, our point groups will be D infinity H and C infinity V. Now, highly symmetry is possessed by IH, OH, and tetrahedral is highly symmetrical. Low Ci and C1 is the low symmetry, whereas rotation with the perpendicular C2 is possessed by the DNH, DND, and DN.
Like this, at each and every step, you will be asked questions, and if your answer is yes or no, then you go according to the arrow which is marked for yes and no. And that scheme finally will take you the exact point group of the molecule. And this scheme is very easy to follow. Simply the scheme asks you the questions. You have to just by looking at the molecule, the shape of the molecule, you have to decide your answer yes or no, and that finally you will go to the point group. Again, I will just mention it is very important before going to the next step, you must verify whether the symmetry elements present in the molecules are correct or not. Otherwise, you will be misled to these different point groups. Now, in order to explain this flow chart as shown, we have to take certain examples to explain this. Now, this scheme, this flow chart does not include the highly special point group, octahedral, tetrahedral, icosahedral. These are not included into this molecule. Now, in order to explain this scheme of classification, let us discuss some example. Now, in this module, some of the examples have been discussed. I will take only few of them, and now after that you have to do the practice. Let us take the first example of CHFBrCl, like this molecule we take. Let us start by using the flow chart. That is, we write down the molecule, and now my question is whether it is linear or not. You will say no, it is not a linear mode. Does the molecule have 2 or more CNXs of greater than or equal to 2? Your answer will be no. Then the molecule does not have any of the rotation of this type. So it does not have any proper axis of rotation. Does the molecule have sigma? That is, if I pass like this, no, this not. If it is like this, it is not. It is not. Molecule does not have sigma. Whether the molecule has center of inversion? No, the molecule does not have any center of inversion. So the molecule belongs to what? C1 point group. That is, no symmetry element present into this molecule. Now let us take another example. Now like this, you go to another molecule, that is PF 5 molecules, and here you can follow this step as shown in, and you reach to the final point group of this molecule. And here 2 examples of molecules are taken, WF5Cl, that is we are taking over here, and just various forms are shown and their point groups can be easily classified. All planes and CNXs etc. are shown into the molecules with the help of the diagram, and it can be easily verified that the point group belonging to this is shown in. Now like this we can take up PF4Cl molecules in the given configuration, and we can reach to the point group for these molecules. At each and every step the question is asked, and you go to the final questions, you will get this is the point group for this molecule. Now I have taken only few examples in which the point groups of the molecules have been taken. But to follow this scheme, you have to do large number of other examples to have the clear-cut idea of the molecule, that is point group of the molecule. In these molecules, we have discussed different geometry of the molecule given in tabular form. 2 schemes of classification of the molecules into the point groups have been discussed. Flow chart is also given. With the help of the flow chart, number of examples have been discussed. Example of PF4Cl in different geometries discussed in detail and point group determined. Now again I will just mention again, to follow this scheme of classification, at each and every step the question asked must be verified before going into the next step, that is whether it is linear or not, that must be verified, whether it has CN axis or NC2 axis must be verified, and then only the success of this flow chart depends. Again, go for the practice as far as possible to get the success of this flowchart scheme. What we have learned so far: point groups of the type 3 and type 4 have been discussed. Examples for type 3, DN, DNH, DN-dipyric have been discussed and cited. Examples of type 4 point group, TD, octahedral, icosahedral mentioned and discussed. Examples of some more special point groups, C infinity V, D infinity H, KH have been discussed, and these have been shown. In all diagrams are given, and wherever are possible, symmetry elements present in them have been shown with the help of the diagram.